let's take another example to further motivate where we're going with all of this. Recall we were talking about the system of linear equations, but systems of linear equations actually have very practical applications of them. So, for example, let's suppose that you're selling two products, product 1 and product 2. So let P represent the collection of products. And what you want to know is, well, how much product of each should I manufacture such that my total amount that I manufacture is within my resources. That is, suppose that I have 3 resources that go into the production of the two products. Resource 1, resource 2, resource 3. All right, so think of this like this. This is cupcakes, these are cookies. This is flour, water, and salt. Obviously, I know there's more that goes into a cookie and a cupcake, but just follow me for the moment, right? So we have 3 resources. Those resources get converted by the baker into either a cookie or a cupcake, right? That's the way we can kind of think about this problem setup here. If we denote xi to represent the quantity of how much of product I we should produce, all right, then the question becomes, well, how much should I or how, not even should, because that's a follow-up question which we'll address much later in this course. The first question is, how much could we produce? So suppose that we have the resources and that we let BK represent the amount of resource K in R we have on hand. So for example, if this represents, let's say, flour, I forgot what I said, but flour, sugar, and water, let's say. B1 would represent the total amount of flour we have, maybe in grams or some other unit we're working in. B2 would represent how much total sugar we have, and B3 would represent how much total water we have. Now, what needs to hold true about our X's and our B's? Well, when we manufacture a single unit of product 1 or of product 2, it's assumed that we're consuming a certain amount of that resource to go into one single unit of the product that's been produced. So we need a quantity to represent how much of the resources are being consumed when we manufacture a single unit of product. And so if we let AIK represent the amount of resource K we consume in producing one unit of product I. And this needs to hold true for all IJ. I'm sorry, all IK, all I in P, and for all K and R, okay? So we have our quantities. We have a very basic model here. Now that we understand how many resources of each resource are consumed for the manufacturing of a single unit of each product, the question now becomes, what needs to hold true? Well, we know that if we have 3 resources and 2 products, that we're going to be consuming the 3 resources. So we have B1, B2, and B3. Now, what needs to be hold true about B1? The total amount of resource 1 that we consume needs to be less than the amount of inventory we have on hand. So the question now becomes, how do we model the total amount that we've consumed? Well, let's again break this down, just like I told you how to break it down in the last homework. What we do is we take the quantity, we first figure out, okay, total. How much is total, right? How much total quantity is consumed here? Well, the first question you need to ask is, what is going into the total? So we know that the total amount of resource consumed is certainly a combination of total consumed by product 1 and then total consumed by product 2, because we only have 2 products. So let's break that down further. Okay, well, how much total resource of how much of total resource 1, only just resource 1, is consumed by product 1? Well, we know that we have a quantity where product, if we make a single unit of product 1, that A11 units of resource 1 is consumed. And if we're manufacturing X1 units of product 1, then the total amount of product that we consume, of resource that we consume through the production of product 1 is just simply the multiplication of A11 times X1. Remember, A11 represents how much of resource 1 that I'm consuming if I manufacture a single unit of product 1, right? So the A's here are kind of like your recipe. If you go to a recipe book, it says, this is for 1 batch of cookies. Okay, the question is, how many batches of cookies are you going to make? Well, you know that if you're making 2 batches of cookies, you're going to double the quantities of each portion in the recipe, right? Well, that's the same general idea here. This is the recipe. This is telling you how much per unit. And these are the number of units. The same holds true for the same resource, but a different product. So A21 times X2. So reworking all of this, we know then, just by breaking the problem down, that A11 times X1 plus A21 times X2 needs to be less than or equal to B1. Okay. And I say less than or equal to, let's change the problem around. Let's say we want to consume exactly all of our resources. So we say equal to. Okay. Next, by the same reasoning, we have a different resource, but same idea. Total amount of resource 2, which has been consumed by product 1, plus the total amount of resource 2, which has been consumed in the production of product 2. We know that there are A1, 2 units consumed for every single unit of X1 produced, and we're producing X1 units. And we know that we have A2, 2 units consumed in the production of a single unit of product 2. Since we're producing X2 of those, total amount of consumed is the multiplication of the 2. And by a similar logic, you can hopefully see the pattern here in the subscripts, which is that we should have that as well for resource 3. So here's a very practical type of problem to use for the system of linear equations. We know that whatever resources we consume, they need to be exactly equal to resources we have. The question is, if we know what the quantities, are for consumption per unit, what then could be the quantities for X1 and X2? Or put differently, we notice we have a system of linear equations here. The solutions are in terms of X1, X2, where we assign them to different numbers. we know that in reality, for a realistic x1 and x2, that all of the equations need to hold true at the same time for different assignments of x1 and x2, because x1 and x2 represent in this model productions of quantities of production. I can't just produce an arbitrary quantity of x1 and x2 because I only have so much. And if I place the restriction and on the production quantities that basically say I want to exactly consume all of my resources through the production of x1, x2, then I only have specific x1s and x2s that I can solve for. We again have those three situations, right? We either have no solutions where there's no production quantity that will allow me to exactly consume all of these quantities. We have one unique solution where there's only one way to produce a certain x1 and x2 such that they all exactly consume. Or we have an infinite number of possibilities. In this case, we say that the system, in practical terms, tends to be over-constrained. What this means is that in our modeling approach, we have placed a lot of restrictions on our decision-making, because this is our decision-making right here. We've placed a lot of restrictions on our decision-making, so much so that we have no possible combination of x1, x2 that we can assign to numbers to get an answer. On the other hand, if we go the other way, we say that we're under constrained. This means that basically we haven't considered enough restrictions in the real world to get us an exact answer. There's more than one possible x1, x2 combination that we can use, and the decision of which to use is going to depend on a constraint that we haven't considered or another objective of the decision maker. In other words, put very simplistically, if let's say I can produce 2 and 3 units, or I can produce 5 and 1, and I don't know if that's correct or not, but just assume those are two possible production quantities that I can use, and they'll both get me this. They'll both allow me to consume all my resources at once. The question is, which should the decision maker pick? Both decisions are perfectly okay. In which case, then it's up to the decision maker's subjective judgment. Either the decision maker will go back to the analyst and say, "Hey, consider this constraint," or the decision maker will use some other type of criteria observing these two solutions to figure out, well, which one do I prefer more? The analogy here is, if I have two routes to send my trucks down to deliver my product to my customer, and both routes cost the same amount of money, and they take the same amount of time, and they're the same amount of mileage, which route should I take? In which case, we're going to use some other restrictions that were not originally considered in the model for that decision maker to make a decision. So that's the moral of the story, right? Is that in terms of the practical implication of the systems of linear equations, we have the theoretical, which I described in the last video, but then we have the very practical notion of what these mean. What do these equate to in the real world? They equate to what we refer to as constraints. And we talked mildly about this in our last lecture with respect to the modeling process. A constraint is anything that we place on our decisions that must be true if we assign the variables to numbers, or more generally, values. So constraints allow us to represent real world quantities that are going on in the real world. So we can't just say let x1 and x2 represent how much we're going to produce, how much should we produce. We also can't just look at a profit equation to make that decision. We also need to take into account, well, what are our resources look like? Because most likely in production, we're constrained. We're constrained by how much inventory we have, how many customers we have, how many orders we have, how much labor we have. We're constrained by the amount of electricity in our building. How many workers from that pool of laborers are able to actually be assigned to the machine to work on that day. The time of day to be able to work, there's some restrictions. Perhaps the shop is unionized. There may be restrictions as per the union contract that restrict matters of production. So there's real world constraints. You can't just say, let us decide to produce this much. No, you need to reflect those constraints on your decisions through in your modeling here. And the way we typically do that is through the use of systems of linear equations. Okay, so in terms of the modeling approach with respect to application, we look at this all the time. Now, they have to be linear. If they're non-linear, we're talking about a different subject matter altogether, which we're not getting into. But generally, the application needs to be linear. With this said, we'll move on to discussing some of the more definition-related items here, because I have not yet defined the concept of a vector or a matrix. But in our next video, we're going to find a way to make all of this math look a lot more neat.